Lesson 55 turned expectation into a single integral. E of x equals the integral of x dp. That sets up the question every limit theorem in this course quietly leans on. Suppose a sequence of random variables xn converges to x. Does the expectation follow? Is the limit of e of xn the same as e of the limit? It is tempting, it gets used constantly, and it is not always true. Here is how it fails. Let u be uniform on 0 to 1, and define xn to equal n whenever u is less than 1 over n, and 0 otherwise. A tall, thin spike sliding toward the origin. Pointwise xn goes to 0. Fix any outcome u greater than 0. As soon as n passes 1 over u, the spike has slid past it, and xn of u is 0 from then on. So the limit variable is identically 0, and e of the limit is 0. But every single expectation equals n times 1 over n, which is 1. The limit of the expectations is 1. The expectation of the limit is 0. The mass never vanished. It escaped upward, growing exactly as tall as it grew narrow. The first theorem that rules this out is monotone convergence. If the xn are non-negative and increasing x1, at most x2, at most x3, and so on, and they converge pointwise to x, then e of xn increases to e of x. The swap is always legal. Monotone means nothing can slide away. The sequence only ever climbs, so no mass can slip out sideways or upward unnoticed. And there is no finiteness requirement. If e of x is infinite, the expectations simply increase to infinity, which is still the right answer. You have already used this theorem. Stage 2 of last lesson's construction defined the integral of a non-negative x as a supremum over simple functions below it. Monotone convergence is exactly what guarantees that supremum behaves, that climbing simple functions carry their integrals up to the right limit. The second theorem drops monotonicity and asks for a ceiling instead. Dominated convergence. If xn converges to x pointwise and there is a single random variable y with the absolute value of xn at most y for every n and e of y finite, then e of xn converges to e of x. Think of y as a lid, one integrable envelope holding every xn at once. Under that lid, nothing in the sequence can ever grow tall enough to carry mass off to infinity. Look back at the spikes, and you can see precisely why they failed. Any y dominating all of them has to be at least 1 over u, and the integral of 1 over u across 0 to 1 is infinite. There was no integrable lid, so dominated convergence never applied in the first place. And when neither theorem applies, one inequality still survives. Fatou's lemma, e of the lim_f of xn, is at most the lim_f of e of xn. For the spikes that read 0, is at most 1, true, and sharp. 2 licenses to swap a limit with an expectation. Monotone convergence, non-negative and increasing to x, and e of xn climbs to e of x. Dominated convergence, pointwise convergence, underneath a single integrable lid y. Without one of them, mass can escape to infinity, and the limit of the expectations tells you nothing at all about the expectation of the limit. Next, the Radon-Nikodym derivative and conditional expectation as a projection, the result that turns the word given into geometry and caps this track.